An ASML scanner can expose a pattern into photoresist on a wafer, but a pattern is not a transistor. The fab must transfer that pattern into material, downward, layer after layer, while protecting everything beside it. Plasma performs much of that carving. Lam Research builds systems for etch, deposition, clean, and dry resist processes around those structures. Its advantage is not one spectacular machine. It is control across repeated wafer steps. And as chips become three-dimensional, that quiet job becomes harder and more valuable. Think of lithography as drawing a stencil. Etch turns the stencil into a structure. A chamber creates a plasma, a controlled mix of charged particles and reactive chemistry. The process removes selected material while trying to preserve the mask, the layer underneath, and the sidewalls. Some recipes push mostly downward, others remove material sideways. Atomic layer etch can remove only a few atomic layers in each cycle. The challenge is not simply cutting small, it is cutting the intended shape uniformly across an entire wafer, then repeating it across thousands of wafers. That repeatability becomes brutal when flat devices turn into three-dimensional ones. A nanosheet gate all-around transistor wraps its gate around stacked silicon channels. 3D NAND drills channels through hundreds of material layers. Some advanced packages, including HBM, connect stacked dies through tall, narrow vertical paths. Each structure demands a different balance of direction, selectivity, depth, and surface protection. A tiny angle error near the opening can become a much larger displacement at the bottom of a deep feature. Lam expects the shift toward three-dimensional devices to roughly double deposition and etch intensity. That is the first payoff. Even if node names stop shrinking, manufacturing complexity can make process steps more numerous and difficult. If you want the semiconductor process behind the AI headline, subscribe. Etch is the center of this story, but Lam is broader than an etch chamber. Deposition tools add films atom by atom or layer by layer. Clean systems remove residues that can become defects. Ether dry resist supports advanced patterning before the pattern is transferred. Copper deposition connects dies in advanced packages. Then customer support teams maintain, upgrade, and tune an installed tool base inside working fabs. Lam reported about $23.2 billion of revenue in fiscal 2026, up 26%. Roughly $8.3 billion came from customer support-related revenue and other. That installed base relationship matters because production tools may run for years while recipes, parts, and requirements keep changing. The business is therefore not a single tool sale. It follows the process from development into years of production. Three structures show why. First, 3D NAND. Its memory channels can be around 50 times as deep as they are wide. A tiny bend changes electrical behavior across the stack. Lam says its Cryo 3.0 process can etch channels up to 10 microns deep with less than 0.1% profile deviation. At 2.5 times conventional dielectric etch, those are company-reported platform results, not a promise for every recipe. Second, gate-all-around logic. Selective etch must remove sacrificial material around silicon nanosheets without consuming the silicon that remains. Selectivity protects the device as much as geometry defines it. Third, advanced packaging. In HBM and some packages, through-silicon vias and copper interconnects carry signals through stacked dies and fragile structures. Different devices, same theme. Add or remove material in exactly the right place and nowhere else. So where is the moat? It begins with a recipe, but it grows through qualification. A chipmaker spends time and wafers integrating one chamber into a specific process step. Sensors, chamber history, cleaning cycles, materials, and upstream conditions all affect the result. Lam's own annual report says that once a supplier's equipment is qualified for a production application, customers generally keep using it for that application and technology node while it performs to specification. Replacing the tool means repeating expensive integration work. That stickiness is powerful, but it is specific to an application. It is not permanent ownership of the customer. The support business reinforces that relationship through parts, upgrades, and field service. The moat is therefore accumulated process knowledge attached to a qualified production line, not a machine that no competitor can build. Important does not mean untouchable. Lam names Applied Materials, Hitachi, and Tokyo Electron as primary etch competitors. A rival can win the original qualification or compete on performance, productivity, and cost. Equipment is also cyclical. When memory or foundry customers cut capital spending, demand can fall quickly. Policy adds another fault line. 34% of Lam's fiscal 2026 revenue came from fabs located in China, while United States export controls limit which tools and services can reach some Chinese customers. Those restrictions can reduce Lam's revenue opportunity and may give some international competitors an advantage. Finally, product announcement numbers are application-specific. A deep NAND channel, a nanosheet release, and a packaging via are not the same etch. Lam's strength is breadth across difficult steps. That breadth is not immunity. Here is the verdict. ASML helps define the pattern. Lam helps turn patterns into physical structures, then keeps those steps repeatable in production. As logic, memory, and packaging move upward and sideways, the AI chip race is no longer only about drawing smaller lines. It is about carving deeper, depositing more precisely, and protecting what must remain. That makes Lam's process control role increasingly important. It does not make Lam a monopoly. The pattern may begin with light, but the chip emerges through controlled material change. To see how fabs find defects after etch, watch KLA, whose inspection and metrology systems help advanced fabs.